So there will be delay of 15 to 20 seconds depending upon our bandwidth. So
there is a delay here.
yeah, we are live. Yes, sir, we are live. I just wanted to check the audio, sir.
We are lagging too much.
Yes, sir. Lag is there, sir.
So this is an internet lag, right?
Yes, sir, internet lag, sir.
Okay.
Are you able to share the audio? My internet is not that good. Yes, audio is coming, sir.
You're able to log in, na?
Yes, sir.
Yeah, we are able to see.
Acha, acha, okay,
Yes,
that's good.
So
Do you have a
audio is
earphone?
coming, sir. So no problem, sir. Audio is coming, sir.
Audio is coming.
Yes, sir.
Okay.
So we are live, sir. We can start the session, sir. So you can introduce and start answering those questions, sir. And then again, they will be posting it here also.
Shall I start answering this question?
Yes, sir. You can start, sir.
See, it is not that I have to answer all questions.
Yes, sir. You can skip the questions, sir.
Which I don't feel it to be appropriate.
Yes,
I can
sir.
skip
You
it.
can skip, sir. Even here also, whenever the questions, no, sir, which you don't want to.
So it's lagging.
Yeah.
So shall I start now?
Yes, sir. You can start, sir.
Hello and welcome to the live session on fundamentals of electric drives. I am SP Das from Department of Electrical Engineering, IIT-Kanpur. So I'll be happy to take up your questions, some clarification regarding this course. Now, we already have a few questions which have been posted by some of you, some students and faculty members. I would like to take up these questions which have been already posted before we take up new questions. The first question which have been asked is mathematical modeling of Swiss reluctance motor drive. Actually, the Swiss reluctance motor we are modeling by an RL load. It is basically the winding of a stator, which are the resistance and an inductance. But however, in this case, the inductance is constantly changing because the stator winding sees poles and slots of the rotor. So this is actually a system with the changing parameters. So the inductance is varying here, and we don't have any equivalent circuit to simulate this as we have for a three-phase induction motor. We have to analyze, if we want to analyze the machine, the Swiss reluctance motor, we have to take the help of something like an ANSYS simulation or a field theory simulation, in which we can simulate the inductance variation, and when we apply the voltage, what is the current variation with inductance. We also cannot apply the principle of generalized machine theory to Swiss reluctance motor because this is a motor with double saliency. First of all, the stator is not distributed winding. The stator is a concentric winding. And the MMF is not a sine wave. MMF is something like a rectangular wave. So we can't apply the principle of generalized machine theory. So we don't have an equivalent circuit for a Swiss reluctance motor. So we have to analyze this motor by applying field theory, taking the help of some simulation software. I have the second question with me that says that in closed loop control of drives, the speed is sensed as feedback parameter. How do we assume that the output of speed controller is current? Now, when we go for closed loop speed control, we have a reference speed and we have the feedback speed, that's actual speed, and we have a speed error. Now, speed error is a measure of how much torque is required to drive the motor. If the speed error is small, the amount of driving torque required is smaller. If the speed error is large, the driving torque required to accelerate the motor will be larger. And hence, the speed error and the torque are related. And we also know that for a motor, torque and current are related, especially in case of a separately excited DC motor. The torque is proportional to the armature current. with a constant field current. Therefore, when we give the input a speed error to a PI controller, the output of the PI controller is essentially torque or armature current. Now, I have another question which says that in a multi-quadrant operation of induction motor, VDC is sensed at the feedback parameter and the controller outputs the ISM. ISM means the maximum stator current. How do you assume that the PI controller gives ISM? Now, visualize the multi-quadrant operation of motor. So in this case, what we have here is the following, that we have one converter in the front end. Here we have, I'm just drawing in terms of the block diagram. It's a three-phase circuit. This we are talking about multi-quadrant operation of induction motor. We also have another converter which is at the motor end. Now this converter is an IGBT converter which is feeding the motor. This is an induction motor and this is being fed by second converter. These two converters are basically joined by a DC link. And the voltage of the DC link is VDC. Now, the input side we have connected to the grid. So we have the grid here, the supply voltage, the three-phase grid. So these are the connections for this. We have the three-phase grid in the input side, and the phase voltage of the grid is, let's say, VAS, VBS, and VCS. And the input current of the grids are IAS, IBS, and ICS. This IAS, IBS, and ICS are not the stator current. These are the input current of the grid. Now, when we draw the control, this is actually called the converter 1, or we can call this to be the front end converter. And this is converter 2. This is called the load end converter, or we can call this to be the motor end converter. So the DC link voltage is basically charge or discharge primarily by the front end converter. Now when we draw the control block diagram, what we do here, we try to keep the DC link voltage constant. So we have a reference DC link and we compare that with the actual DC link, and we have a PI controller, and the output of the PI controller goes to a limiter. This is a limiter, and this decides, the limiter output decides the maximum value of the input current. So this ISM is not the stator current, I would like to correct here. It is the input current of the supply. So ISM is the peak value of the input current. ISM is the peak value of the input current. Now, why so? Because this error, the error in the VDC decides whether the capacitance is to be charged or is to be discharged. And the front end converter is a bidirectional converter. It means this can supply power to this side for the motoring, and this can also reverse the power for braking. So it means the input current decides the voltage of the capacitor. So this capacitor voltage error, VDC star minus VDC, this is a VDC. We can have a feedback here. We can have a voltage sensor which will sense the VDC and will feedback to our control. And this ISM decides whether the energy has to be or power has to be fed from the source to the capacitor side or from the capacitor to the source side. And that is why the voltage error decides ISM, and ISM is the peak of the input current. I hope I have clarified your question. So let's go back to our discussion. So I also have another question. It says that in closed loop speed control for a load commutated synchronous motor drive, what is the significance of sign of the speed error that is fed to the phase delay block? Now we know that if you visualize the load commutated synchronous motor drive, for motoring, the converter from the DC link to the synchronous motor operates in an inverting mode. It's a thyristor converter, and the converter is commutated by the back EMF of the synchronous machine. And the triggering angle alpha in that case is from 90 to 165 or 170, which is the alpha maximum. Now, when we want to go for braking, how do you know that it is undergoing braking? For braking, the speed is lower than the reference speed. So the error is negative. So for the braking operation, the same motor side converter will be functioning as a rectifier. It means the motor is now functioning as a generator, and the supply is basically fed from the motor side. So for a rectification operation, alpha has to be between 0 to 90. So the polarity of the speed error decides whether the motor is to be operated under motoring region or braking region. That's why the polarity is important. We have another question from a faculty. We says that using slip power recovery scheme, how braking operation can be achieved below and above synchronous speed. Now we operate the motor under slip power recovery, that is basically for slip ring induction motor, especially for very high power application. Usually slip ring induction motors are not commonly found in our day-to-day application. Majority of the induction motor used in the industry are squirrel cage induction motor. Slip ring induction motors are used only for high power, especially close to megawatt range. So in that case, we are not interested in transient performance. We are only interested in speed control. Let's say speed control of a fan, a big, huge fan, speed control of a huge blower. There we are not interested to go for braking. We're interested to control the speed slowly. We're interested in steady state speed control. So in static rammer drive, the application demands that we need to control the steady state speed. We don't go for usually braking. We go for steady state speed control. There's another question from another faculty member. Which says that for single phase full control rectifier drive in continuous conduction mode, discontinuous conduction mode, no load speeds are given by Vm by K for alpha from 0 to 90 degree, and Vm sine alpha by K for alpha between 90 to 180 degree. he is asking how it is so. Now, let us just go back to our circuit diagram. Now, if we see our circuit diagram here, uh, okay. Now, in case of a full controlled rectifier, so what we have here is we have the rectifier bridge, and we have a motor load. The motor load means we have a resistance, we have inductance, and we have a back EMF. This represents the armature of a DC motor, RA, LA, and we have the back EMF. On the input side, we have the AC supply. The AC supply is given like this. We have, this is the source voltage, and Vs is equal to Vm sine omega t. Now let us draw this waveform. So this is the part of the input voltage waveform. So we are plotting omega t here, and then this is pi, this is 2 pi, and let's say this is our back EMF. When we trigger at an angle alpha, so this is our alpha here. For discontinuous current operation, our output would be somewhat like this. This is the output voltage. So this is a repetitive. So we have like this. Now, what about the current? The current actually starts from alpha and then it ends at a beta. So this is the value of, this is the extension angle, that is beta. And again, it is triggered at pi plus alpha. So the triggering instants are alpha, and then we have pi plus alpha. So this is the voltage output. Say we call it VA here, and this is the armature current, that is IA. So this is VA, and then we have the armature current here is IA. When alpha is between 0 to 90, the maximum supply voltage can be Vm. So maximum supply voltage is equal to Vm. It means it is not necessary that if we trigger at an angle alpha, the SCRs will go into conduction. SCRs going into conduction is decided by the triggering angle alpha and also the back EMF. The SCRs have to be forward biased. So for SCR has to be forward biased, we don't usually trigger the converter by a single pulse. Rather, we trigger the converter by a train of pulses. So we trigger by a train of pulses, and the duration of the pulse train is 90 degree. So now even if we trigger at alpha equal to 0, the conduction may start something like alpha may equal to 30 degree or 45 or 60, depends upon the back EMF. Now we are saying that it is truly under no load condition. What is the meaning of no load? No load means armature current equal to 0. So the no load implies IA equal to 0, absolutely. So which means the back EMF has to be equal to the peak of the supply voltage. Peak of the supply voltage. and that's equal to Vm for alpha between 0 to 90 degree, and that's equal to Vm sine alpha for alpha between 90 to 180 degree. Okay, so from alpha to 0 to 90, the peak of the supply is Vm. This is Vm, the peak of the supply voltage. And from alpha 90, this is 90 or pi by 2. From alpha 90 to 180, the peak of the supply is Vm into sine alpha. Alpha is the instant of triggering. So if E equal to Vm for alpha between 0 to 90, this implies the no load speed omega m naught equal to Vm by K. And if the peak of the supply is equal to Vm sine alpha, this implies the no load speed is equal to Vm sine alpha by K. So this is the reason why the no load speed depends upon the alpha, and from alpha between 0 to 90, the no load speed is Vm by K, and alpha between 90 to 180, the no load speed is Vm sine alpha by K. I hope I have clarified your question. So we'll go back to, let's say, the new questions if there are any. Okay. Now, if you have done the assignments sincerely, you should be able to answer the question paper. The style of the questions will be something similar to that have been given in the assignment. Exam paper pattern, I have already said that. Something which have been given in the assignment, the way the assignments have been framed, similar pattern will be the examination question. Okay. I want to know about the torque ripple of a low-cost unipolar BLDC motor. It thrice the rotational frequency. Now, the thing is this, that if you see the BLDC motor, the low-cost BLDC motor. So let's see why the ripple frequency is opaque John for 240. So we have the windings, which you can see in the lecture notes. Delta varies between 120 to 0 degree. We have an electromagnet. The electromagnet is being attracted by the stator. The stator is energized by DC voltage and 3 transistors. If you remember the circuit, that we have the DC voltage here, and we have the stator windings like this. Let's say phase A or phase 1. Similarly, we have the second winding, and we have the third winding like this. Okay. Now this is the structure of a low-cost DC motor, and we are talking about a simple two-pole structure here. So we are talking about a simple two-pole structure. So number of poles equal to 2. So if the number of poles equal to 2, here we are having thrice in one cycle the switching. The switching takes place thrice in one cycle, one electrical cycle. And for a two-pole motor, one electrical cycle is same as a mechanical cycle. So since in one electrical cycle we are having 3 switchings, the torque ripple is 3 times the rotational speed. But this is true for two-pole structure. If the number of poles is different from a two-pole, then accordingly the ripple frequency will be different. The torque ripple will be different. But for a two-pole structure, the torque ripple will be 3 times the rotational frequency, because in one complete cycle, we are having 3 switchings. So let's go back to our discussion. Okay, is there only MCQ? I have already asked this, answered this question about the examination pattern. So you have to sincerely solve the assignment question papers. If you haven't solved the assignment, I urge you that each one of you who are taking the examination should solve all these 8 assignment questions. Okay. I think I have answered all the questions that are being posted. So is there any new questions? So this is basically fundamentals of electric drives. This is basically fast course in drives. There is also another course available, which is the advanced electric drives. If some of you are interested, this is also available in the YouTube, so you can just have a look at the various lectures. That basically deals with the advanced analysis of both DC and AC machine, but mostly the AC machines, which means induction, synchronous, and permanent magnet synchronous machines. Yeah, so if an unbalance created in the rotor circuit of an induction motor, which is started from rest, how the motor speed will settle to a value close to half the synchronous speed? This is a very good question. Okay. Now, here the unbalance is in the rotor side. Okay. Now, if the unbalance is in the rotor side, the rotor is the source of harmonics. The rotor is the source of unbalance. So usually we do unbalance in the stator side. But if there is unbalance in the rotor side, the rotor field is a single phase field. So instead of a rotating field in the rotor, we have a pulsating field in the rotor. So the rotor pulsating field can be divided into a forward rotating field and a backward rotating field in the rotor. So those fields will interact with the state of the rotor. So this is our rotor circuit, and we have the stator here, 3-phase stator, and the rotor is single-phased. Maybe some of the bars are removed. We have an unbalanced rotor, right? So if we have an unbalanced rotor, the rotor field is a pulsating field. So this becomes a single phase field. Now usually the motor is rotating in the forward direction. This is the rotation here, omega m. So the slip of the motor is S. So the slip frequency is S into F. So the induced voltage or induced current in the rotor side is S into F. Now we can have a forward field, we can have a backward field. The forward field will rotate with S into omega S frequency, omega ms, and the backward field will rotate with minus S into omega ms. So we have this is called the forward rotating field. And we have a backward rotating field. Now, if you have a forward rotating field, what happens here is that this forward rotating field will be rotating at certain speed. So with respect to the stator, this is our stator here, and we have the rotor in this case. So with respect to the stator, this field will have the following speed. The rotor speed is omega m, and the forward field is S into omega ms. So that's equal to 1 minus S. This is forward rotating field. 1 minus S into omega ms plus S into omega ms. So that's equal to just omega ms. So the rotation or the forward rotating field rotates at the same speed that of the synchronous speed. So our synchronous speed is omega ms, and so the forward rotating field produces the same effect that of the normal stator field, because the forward rotating field is also rotating at the same speed, that is omega ms. What about the backward rotating field? The backward rotating field is rotating at minus omega ms. So what is the speed of the backward rotating field with respect to the stator? The backward rotating field is minus omega ms. This is for the backward rotating field, omega m minus s into omega ms. So what is this one? So this is 1 minus s into omega ms minus s into omega ms, that is 1 minus 2s into omega ms. Now let us try to understand what it does basically. Now s is a quantity which is varying from 1 to 0. Okay. So when is s equal to 1? S equal to 1 is at the starting. And when is s equal to 0? S equal to 0 at synchronous speed. Now if s equal to 1, what is the speed of the backward rotating field? Let us substitute s equal to 1 here. So what is the speed of the backward rotating field? It's equal to 1 minus 2 into omega ms, right? That's equal to minus omega ms. So it is very interesting to note that the rotor speed or the rotation of the backward rotating field is minus omega ms. So it is basically, this will also produce the same positive torque as that of the normal forward rotating field. Why? Because this field is being produced by the rotor. So the motor will be behaving as an inverted induction motor. It means if we apply a field to the rotor side, the rotor will rotate in the opposite direction to the rotation of the rotating field. Now in this case, this is minus omega ms, so the rotation is positive. So a negative field will create a positive rotation, because this is an inverted machine. So the backward rotating field will also produce a forward torque, and the motor will try to rotate in the forward direction. But however, we can see that the speed of the backward rotating field is sleep dependent. It's a function of sleep. So as the sleep goes on increasing, decreasing from 1 to 0, this negative speed will gradually decrease, because from s equal to 1 it will be s equal to 0.5, maybe s equal to 0.25. If s equal to 0.25, it will be 0.5. So say for example, if you have s equal to 0.25, what is the speed here? 1 minus 2 into 0.25 into omega ms, that's equal to 1 minus 0.5 into omega ms, that's equal to 0.5 omega ms. So this speed is gradually becoming less and less. Let's say s equal to from 1, let's say it is 0.75. So if it is 0.75, this is 0.75 here. So what you get here is 1.5. So it is minus 0.5 omega ms, but still it is negative. So the rotation is positive here. Now exactly at s equal to 0.5, the speed will appear to be stationary, because this is 1 minus 2 into 0.5 into omega ms, that's equal to 1 minus 1 into omega ms, that's equal to 0. So at s equal to 0.5, the speed will be stationary, there is no torque. Because if the rotating field is stationary, no torque is produced by the stationary field. So exactly at s equal to 0.5, the contribution of the reverse rotating field will be 0. Now, what happens if s is still reduced? If s is 0.25, the speed, the reverse rotating field or the backward rotating field will have the speed that's equal to 1 minus 2 into 0.25 into omega ms, that's equal to 1 minus 0.5 into omega ms, that's equal to 0.5 omega ms. So the speed of the rotating field has become positive from negative. So it is an inverted machine. If the speed is positive, the motor torque will be negative, and so on. So we can draw the overall equivalent, overall torque speed characteristic. So if we plot the overall torque speed characteristic of this motor, so let me plot here torque in the x-axis, y-axis, and speed in the x-axis, omega m in the x-axis. So this is s equal to 0, and here s equal to 1. So this is the normal torque speed characteristic for a normal machine. Now for a with the rotor, so this is for the forward rotating field. What about for the backward rotating field? Up to s equal to 0.5, the torque is positive. So if the torque is positive, so it behaves as a normal induction machine like this. At s equal to 0.5, this becomes a stationary field, which is 0 speed. So the torque is 0. And from 0.5 to this is s equal to 1 to s equal to 0. Sorry, this is s equal to 0 here. Now from 0.5 to 0, the speed of the backward rotating field becomes positive. So the torque will be negative. So if the torque is negative, the torque will appear like this. And what happens at s equal to 0? Let's see, if you have s equal to 0, what is the speed here? 1 minus 2 into 0, right? 2 into 0 into omega ms, that's equal to omega ms. Anyway, when the speed is a synchronous speed, there is no induced EMF. When the speed of the motor is a synchronous speed, there is no induced EMF. So there is no question of either forward rotating field or reverse rotating field, because the reverse or forward is being produced by the rotor current. Rotor current itself will become 0 at synchronous speed. So the torque here will be equal to 0. So let us draw the overall torque. The overall torque is the sum of this torque. This is for the backward rotating, forward rotating field. This is for the backward rotating field. The overall torque here is the sum of these two torque, which is like this. Okay, and then it basically will come down and will become negative and will again be 0 here. Now, if you have a load torque, suppose you have a load torque here. Let's say this is our load torque. Okay, if you have a load torque like this, normally what we have is that the operation is somewhere here, okay, which is close to the synchronous speed. Now, if you have single-phased the rotor is unbalanced here, our operation will be somewhere here. And this operation is close to half the synchronous speed. This is precisely the region where the speed will be close to the half the synchronous speed. I hope I have answered your question. Okay, now coming back to more questions here. Okay, if you are asking, okay, there are questions possible to post lecture notes. Okay, I will see if it can be. I don't have any the typed lecture notes. I have the handwritten lecture notes. I'll see if I can, but I'm not able to promise that. But I again ask you, suggest you to solve all the assignment problems. Okay, question 12, and answer is nearly 600, given assignment number 6. I'll check, because this assignment has been checked. I'll make a note of it, and I'll check this once again, because I don't have the assignment with me right now. Assignment number 6, question 12. Answer is near 600, but it is given 700. We have already checked the answers, and wherever correction is possible, we are notifying the correction. Possible all the lecture notes along with the video lecture. I'll see if the handwritten notes can be made available, but I'll just make an attempt. But typed notes may not be possible at this short notice. We will post link. Okay, assignment number 7, question number 15. The another assignment related thing, assignment number 7, question 15. Is there any clarification on this? We'll get back to you. Actually, it will be posted, right? We'll be posting this. I'm noting down. Answer is option C. I think so. I think this has been already clarified. Yeah, that's correct. That's correct. Answer is 15. I think these questions were related to the margin angle, right? I think we have already given the reply. And if you have marked the answer C, anyway, these questions actually will be reevaluated, and due credits will be given for this question. Okay, again, actually, there is a request for the lecture notes. I will try to post the handwritten lecture notes. Okay. Yeah, I think these are the questions. So I think we should be able to scan our lecture notes, and we should be able to post the handwritten lecture notes. So wherever there is an error in the or any clarification in the assignment, we are notifying this. Okay, but still this assignment 6 and 6 question number 12 will check. So I think we have exhausted all the questions.
Yes.
Right?
Yeah. Let's wait for 2 more minutes. In case if they are not posting any questions, we'll end the session, sir.
So if you have any more questions, you can ask. But I understand that many of you will be interested to have the lecture notes. We'll try to upload the PDF of the scanned lecture notes at the earliest.
Assignment 6, question number 12, I'm having it, sir. Like in case if, but the battery is very, you're able to view, sir? No, sir.
Can you increase the brightness?
Yeah, actually, battery is low, so
Okay.
Let me just see, sir. Shall I read, sir, or else?
400
400 volt, 50 hertz, 6-pole induction motor is controlled by a static Kramer drive. The stator to rotor turns ratio is 3, and the primary to secondary.
It has to be, yeah. I think this question, okay. This question assumes turns ratio equal to 2. Okay, these questions will be reevaluated for your information. Yeah. these questions will be re-evaluated. Assignment number 6, question number 12. Yeah. There is a question on, will there be any course on advanced electric drives? Okay, I'm not very sure whether I'll be offering that course because we'll see about the commitments also. But for your information, the lecture videos of advanced electric drives are available in the YouTube. So if you are interested, you can just go through some of the videos of advanced electric drives. Whether it will be offered in the next semester, I'm not very sure. I have to talk to the coordinator and I'll just see what can be done, but I'm not very sure at the moment. There are another questions on the net being slow actually. I don't know whether.
Yes, sir, I replied to that.
Okay, you have already
question, sir.
replied.
Yeah.
Okay.
So after this event, we will make an announcement, sir.
Okay. This will be available
Yes, I will be
for
available,
viewing,
sir.
right?
Yes, sir.
Okay. Yeah, regarding the paper style and the question paper, etc., it will be somewhat similar to the assignment that you have been solving every week. So that answers questions of exam pattern also. So you have to solve the assignment problem sincerely and independently. Okay.
Can we end the session, sir?
Yeah. So if there are no more questions, so thank you very much for participating in this session. So wish you all the best for the exam. So I want to close this session because there is no more questions now. So thank you.
So we'll stop the stream, sir.